Hello and welcome to today's ACM Learning webinar. This webcast reflects ACM's deep commitment to lifelong learning, aiming to empower computing professionals and students who join ACM's worldwide community of 100,000 plus members. My name is Eugene Fiume. I'm professor and past chair of the Department of Computer Science at the University of Toronto, where I'm involved in the Dynamic Graphics project, and I'm director of the Masters of Science in Applied Computing program. I was also Director of Research and Usability Engineering at Alias Wavefront, where I first got to know our speaker today, Alain Chesnais, and I now advise several companies on both technological and business issues. I've also been heavily involved in ACM and ACM SIGGRAPH activities, serving as Papers Chair for SIGGRAPH 2001, and I'm past chair of the SIGGRAPH Awards Committee from 2003 to 2008, and the Paris Kanellakis Awards Committee of ACM in 2011. I've also been involved in various symposia associated with ACM and SIGGRAPH. Now, ACM offers innovative educational and professional development resources that bolster skill sets and enhance career development opportunities. Our members are able to stay competitive in the dynamic computing world with a range of ACM Learning Center online resources at learning.acm.org. You can see some of the highlights on your screen. ACM recognizes the role of computing in driving the innovations that sustain competitiveness in a global environment, together with timely computing information published by ACM, including communications of the ACM and Q magazines, access to the ACM Digital Library, the world's most comprehensive database of computing literature, and international conferences that draw leading experts on a broad spectrum of computing topics. Support for education and research, including curriculum development, teacher training, the ACM Turing and ACM Infosys Foundation Awards. ACM enables its members to solve critical problems using new technology that enriches our lives and advances our society in the digital age. Before we get started, I'd like to mention a few housekeeping items shown on the slide in front of you. Whoops, now I just lost mine. Sorry. There we are. In the top right corner of the slide area on your screen, there's a button that will allow you to enlarge the slides. You may also enlarge the slides at any time by dragging the corner of the slide window. The slides will advance automatically through the event. You can minimize the slide area, Q&A, and bio screens using the buttons on the bottom panel. You can also use a number of widgets also found at the bottom panel, including Facebook, Twitter, Wikipedia, a sharing tool, and a resource list where you can get a copy of the slides. If you're experiencing problems with the program, please press the F5 key on your keyboard if you're using Windows, or the Command +R if you're on a Mac, to refresh your console and close and relaunch the presentation. You can also visit the webcast help guide by clicking on the help widget just below the slide window. To control volume, adjust the master volume on your computer. At the end of the presentation, you'll see a survey URL on the final slide. Please take a minute to fill it out and help us improve your next webinar experience. This session is being recorded and will be archived. You will receive an automatic email notification when it is available, or you can check learning.acm.org in a few days for updates. At the end of our presentation, we will have time for questions, and we hope you will have several. If you think of a question during the presentation, please type it into the Q&A box and click on the Submit button. You do not need to wait until the end of the presentation to begin submitting questions. You may also use the Q&A box and the survey at the end to suggest topics for future webinars of interest to you. You can now use Facebook and Twitter widgets at the bottom panel to share the presentation link with your friends, as well as tweet comments and questions using the hashtag #ACMWebinarWebGL. We'll be watching for your tweets. Today's presentation is The Security Impact of WebGL by Alain Chesnais. Alain Chesnais founded TrendSpottr, which develops web services to identify real-time trends in social media communities such as Twitter and Facebook. Formerly, he was the CTO of Scenecaster.com and Vice President of Product Development at Two Cows, Inc. He also served as Director of Engineering at Alias Wavefront, managing the team that received an Oscar from the Academy of Motion Picture Arts and Sciences for developing the Maya 3D software package. Alain is also past president of ACM, having served the 2-year term beginning 1st of July 2010. Prior to his election as ACM president, he served as vice president and secretary-treasurer. He was also president of the ACM SIGGRAPH and SIG governing board chair. As a French citizen now residing in Canada, he has more than 20 years of management experience in the software industry. Alain joined the local SIGGRAPH chapter of Paris some 25 years ago as a volunteer and has continued his involvement with the ACM in a variety of leadership capacities since then. Alain, we look forward to your presentation here today.
Thank you, Eugene. Okay, let's get over to, see if I get the right slide here. As we wait for the slides to update, okay, not quite. Sorry about that. As we went through, I thought we'd be primed there. Here we go. Okay, so let's look a little bit at how we got to where we are with WebGL. Just to give you all an understanding of what we plan to do here today, we're not going to go very much in-depth into WebGL itself. Basically, the focus will be on giving you an overview and links to places where you can go to get more information so that you can go and fully understand how to use WebGL for your applications and what you might want to do with it. We'll focus on 3 APIs that you can use, and we'll go into the relative merits of the 3 to show you what you might be able to do and how you might use each of them for your applications. Okay? If we were to go into a full training on WebGL, that would be a full-day course. We've only got an hour, so we'll be focusing on the key essential elements, and that's really where this talk will be going. So let's go back in history a little bit and see where WebGL came from and what its predecessors were and how we actually got there. If you go back about 20 years, actually a little bit further than 20 years ago, Silicon Graphics was the leader in 3D hardware in the mid to late 80s and had a library called IrisGL that did more than just pure graphics. Basically, it was a windowing system. It was a whole interaction library, but included a key subcomponent, which was the actual graphics library, what would let you do 3D interactive graphics directly on your workstation. What was happening at the time was there was a plethora of new hardware vendors coming into the field of 3D graphics. Silicon Graphics was probably one of the first, along with Evans & Sutherland and HP, but others such as Sun and DEC and various hardware manufacturers started coming in, and the key issue that we saw at that point was that there were so many hardware vendors that the software developers had a major problem. The issue for software developers was which API to use. Now, at the time, the FIG standard was already available and let you do 3D graphics, but the problem with FIGS was that it was felt to be way too complex for most of the applications that people wanted to use. It worked, but it was a lot of investment and very difficult, or felt to be very, very difficult to use. So the folks at SGI decided that the best way to go and address this was to take the graphics component of the IrisGL API and propose it as an open standard that they would call OpenGL. So they proposed this in 1991. And very quickly, what we found was that this open standard got a fair amount of popularity. But what happened then is various vendors worried that SGI was in control of this standard and looked to see how we might work together so that there would be an independent body overseeing the API calls, something that could go and vet the architecture as it evolved and make sure that it would work well across all the platforms that were concerned. To do that, the vendors who worked and participated in defining OpenGL built out the OpenGL Architecture Review Board, and that was created in 1992, so a year after the release of OpenGL. Silicon Graphics handed over the responsibility of this open standard to this Architecture Review Board that was made up of the key vendors in the field, so everybody who had a stake in making 3D graphics performant and easy to implement could now sit on this board and help evolve the standard. Now, as time evolved, we found some changes coming into the market, and one of the key changes that happened was the move for personal computers to start being able to do high-end 3D graphics. And specifically, Microsoft was the key leader in the field for personal computers looking to do 3D graphics, and they came up with their own library, which was Direct3D. Now, Direct3D was introduced in 1995, and there was a fair amount of tension in the industry at the time between the proponents of OpenGL and the software vendors who really wanted to focus on Direct3D as the method for being able to express 3D content and deliver it on a personal computer. That stayed as an open issue for quite a while, and Microsoft and SGI worked together to launch a project that was called Fahrenheit in 1997 with the aim to provide a unified API across both the workstation platforms, which OpenGL covered extremely well, and the PCs, which Direct3D tended to cover extremely well. Unfortunately, given the constraints of each of the companies working on this, that project fell through, and Fahrenheit was abandoned in 1999. Key change that happened a little bit later with the changes at SGI was that in 2006, the Architecture Review Board voted to transfer the control of OpenGL, so the OpenGL standard itself, to the Kronos group. So this is an independent group that has been set up to be able to go and follow extensions in the world of 3D and oversees the definition and evolution of the OpenGL standard. And they've been doing so ever since. So then we get to a major change in the market, which is the apparition of individual embedded systems. So think of low-end systems such as mobile phones and tablets, and started seeing these systems come up with very high-end graphics capabilities, but serious constraints in terms of memory capabilities and in terms of raw power of the processors on which they ran. Basically, in order to be power efficient so that they could actually run on batteries for a long time, typically you would cut in the absolute compute power of the chips that you would put inside, and some changes needed to be made to OpenGL to be able to address that. And that's what generated a new version of OpenGL, which is OpenGL ES. Now, OpenGL ES, the ES stands for Embedded Systems, again, with the constraints of having to have low power consumption and very, very little memory compared to the big brothers that were the PCs and workstations of the time. The general OpenGL architecture wasn't well adapted to do that. So basically, the whole goal of this architecture was to define a streamlined version of OpenGL that would give the essential functionalities of the 3D graphics library without killing the processors that they were targeting along the way, and allowing them to be power efficient so the batteries wouldn't die out, and you could actually have mobile computing with high-end 3D capabilities built in. The original focus was to the point where the assumption was made for OpenGL ES1 that we couldn't assume that there was even a floating point unit on the chips that we were aiming at. That assumption was dropped a little bit later, where we assumed that with OpenGL ES2, we could assume that floating point could exist, and we could actually write our libraries without having the constraint of going to a fixed point notation to be able to go and represent our values. But in the original version, just to make sure that we could be as efficient as possible, we actually did away with that. As the architectures have evolved, the hardware architectures that is, we've been able to lift that now, and we're able to go and do things a lot more efficiently with higher levels of capabilities than were originally designed into OpenGL ES. We're now at the third release of OpenGL ES, and the key elements that we have in OpenGL ES is the assumption that there's very, very little in terms of, say, fully provided infrastructure for managing all of your matrix stacks, all of the elements that we were used to having in the previous OpenGL were now pushed down to the programmer, so that the programmer's responsibility was now to go and manage all of that logic. It was no longer built into the API itself. That made for an efficient implementation, but comes at a cost. So in 2006, a new proposal came through from the Mozilla group looking to see what we might do within a browser, felt that the architecture that had been designed for mobile devices was actually the right design to be able to adapt to providing a 3D interface within your web browser. The whole idea was to be able to take a structure like the DOM, use a language that is the native language for web pages, that is JavaScript, and take that language to be able to go and show what we could do by actually binding it in a power-efficient manner. So what we do with that is to be able to take the HTML5 proposal for Canvas, so the Canvas element in the HTML specification, which was designed for a programmatic approach to 2D drawing as compared to what the SVG standard did, which was a declarative method. Here, what Canvas would provide, the base Canvas, provided a 2D context, and that 2D context would allow you to draw using JavaScript calls. The proposal from Mozilla was to be able to go and take that and extend it to make what was called Canvas 3D. So provide a 3D extension for this to be able to go and give the programmer a 3D context in which to draw 3D content within a Canvas primitive. So now we had a situation where with this proposal what we had was both a 2D context available and a 3D context available within the Canvas element that programmers could choose from to be able to go and render what they needed to do. This was proposed and brought forward to the Kronos group as a proposal for an extension to do an OpenGL-like extension in JavaScript for the elements that would come forward. What was finally adopted wasn't the Canvas 3D primitive itself, but a modification thereof. Basically, the Kronos group set up to create WebGL, a working group to formalize what was to become WebGL in 2009. They designed it to support the OpenGL ES 2.0 bindings in JavaScript. So the idea is now what you would have is the primitives that were available in the OpenGL ES2 API would now be available from within the JavaScript context to be able to go and render 3D within a Canvas element. So many of the same ideas as what Canvas 3D had originally proposed, but now what we had is a formal open standard being proposed by the Kronos group that would become what we know today as WebGL. The first version of WebGL shipped in 2011, and it was originally supported in desktop versions of Firefox, Chrome, Opera, and Safari. There was one major absentee in the first versions of this, and that was Internet Explorer. Happily, that has changed. What's happened recently is with the release of Internet Explorer 11, WebGL is now supported. That is a really, really important step in the progress of WebGL, because what that means is that now web developers don't have to worry as much as they did before as to whether or not the 3D primitives that they count on to deliver a consistent interface across all the platforms that they might want to target would be available in all of the browsers that they would care to actually support. Now, is it reasonable to expect WebGL to be available in all the browsers? No. For instance, it will never be supported in links. If you look at a text-based browsers, there is no ability to go and do this. But if you can make sure that the browsers that are considered to be the dominant elements in terms of what people currently use out in the field, if all of the major browsers actually support WebGL, we now have a compelling API that developers can use to be able to go and present their 3D content across the web, no matter what major browser you're using. Now, this comes at a price. Again, what we see is all the major desktop browsers currently support WebGL. That's not the case with mobile browsers yet. We're seeing the ability to do it on most of the major mobile browsers, but in most of them, that capability is turned off by default. In certain of the mobile browsers, you still need to enable it explicitly at the user end to be able to use it, and in some, you can't even do that. So say in mobile Safari today, you cannot enable WebGL in the production version, though we can use it in iAds, and we can use it within the development environment to test it out. The expectation is, as the technology becomes more robust and gets debugged more and more consistently, we will expect to see it also on mobile browsers. That's not the case today. Parallel to that, we've also seen a new release of OpenGL ES, which is OpenGL ES 3. And the Kronos group is currently working on the next version of WebGL, which will be WebGL 2, to specify it based on the API defined by OpenGL ES 3. So that describes where we are at in terms of the definition of WebGL. And what I'd like to do now is go towards the resources and point you towards where you can go to learn more about WebGL. Again, we don't have time in a 1-hour session to be able to go and give you a full training on WebGL, but what I can do is show you where the key resources for learning about it are and what are the key implementations that you can look at, and specifically what libraries are built atop core WebGL to facilitate your development efforts so that you can be more productive in terms of what you want to develop with WebGL. So one of the best resources out there right now is a site called learningwebgl.com, which was developed by Tony Parisi, who's been one of the core developers in the OpenGL space. And Tony has done a great job in terms of setting up a series of tutorials that walk you through the key elements of WebGL. So what I propose to do here is to take you through the first tutorial, and we'll go fairly in-depth with that to give you the core elements that you should be aware of in terms of what defines WebGL and how you can use it. And then I'll go very quickly in terms of overviews of what else are in the tutorials, but we won't go in depth in the further tutorials. Okay? So what I'm going to do now is switch into screen sharing mode, and we will go over and show you an interactive session with this, looking at the lessons and looking at code as we do that. So let me launch that now. You may see a little buffering icon while that starts up, and shortly you should be able to see it. So what you should be seeing now is an image. Now this is a 3D rendering of a triangle and a rectangle done with WebGL. And this is the first lesson in Tony's tutorials. And what I'd like to do is take it apart so that we can actually look at the source code and see how it's made up so that you can get the core elements that you need to take away from this presentation to understand what WebGL is all about and how one actually uses it. So I'm going to go and look at the source of this right now. So let me bring that up. Okay, let me go and make that font a little bit larger so you can actually see it. And let's look at the key elements. Okay, so we'll skip over the libraries that Tony is bringing in. This first one here, the GL Matrix library, is a library. It's a helper library to let you do transformation matrices and all the rest that you would expect to be able to do in graphics and handle that. Now let's look at this next block here that I'm highlighting. So here what we're doing is we're defining what's called a fragment shader. So we'll be looking at two classes of shaders in WebGL. And again, for those of you who are familiar with OpenGL, the shaders should be familiar concepts. For those of you who aren't familiar with WebGL, with OpenGL, excuse me, what shaders are is they're functions that are defined in a language that compiles extremely efficiently to the hardware that supports your graphics libraries. So basically what we're going to do is we're going to take a language that looks like C. It's called GLSL, the GL shading language, and has a C-like syntax, so it should be fairly familiar to any of you who have ever coded in C or any of the closely related computing languages, and will allow you to go and represent what you want your graphics processor to do in a high-level language that you can easily manipulate. That will later be compiled and sent in a very, very efficient format down to the graphics hardware so the graphics hardware can apply it directly on all of the blocks of data that it needs to handle. So vertex shaders operate on the endpoints of your elements, and this lets you go and transform geometries and do pretty much anything you might want to do in terms of transformations. Fragment shaders operate on the individual elements that you will be rendering at a pixel level or subpixel level. So there are two classes of shaders. This first one that I've highlighted is a fragment shader, which does nothing more than set the final fragment color to a constant white. That's why we saw that the triangle and the square were both white, constant white, no shading, no fancy lighting, nothing of the sort. We're just applying a constant color directly to this, and that's what this is doing here. Okay? And if you look at the code, it's fairly straightforward to understand what it's doing. There's nothing really overly fancy. The one that may seem a little bit new to those of you who have never seen GLSL is this precision medium P float, which is basically telling the renderer that what we want is medium precision, so 32-bit floats, for floating point values that we'll be handling. Every graphics processor that supports WebGL is required to support medium P. You can also get a higher precision value if you want, and you can set that, but there's no requirement that the processor that you're actually working with will support it, so you may generate an error on that one if it's not able to support it. So now let's go down and look at this second shader, which I'm highlighting right now. So this is a vertex shader that is going to do all of our 3D transformations. Now here there's some interesting elements that we should look at, and I'm going to go into them to point out the particularities of WebGL and what it requires the programmer to do. So basically what we've seen in previous APIs was that a lot of help was given to be able to go and manage your transformation stacks, be able to get your vector positions, your vector transformation matrices, or your perspective matrices set up in a consistent manner. WebGL does not provide that for you. You have to do it yourself. It's up to the programmer to actually do the math to transform the world coordinates into the device coordinates through both the actual change in terms of position elements and the perspective transformation that you can apply using the perspective matrix. So here what we've got is this, here we go. This first one up here, UMV matrix, which we will actually set a little bit further down, is a constant matrix, yes, that we will be setting outside of the scope of this shader. It will come in directly, and then we'll be able to go and apply it to the world positions of each vertex that we actually have, and then we'll compose it by the final perspective transform, so basically a perspective matrix that we have to set up ourselves. Okay, and that's a key element to understand in terms of the level that WebGL provides. WebGL does not do this automatically for you, and that is a key point to take away from here. You have to do it yourself. Okay? So let's go in and look at the rest of the elements to go through and see what's actually happening here. So everything is done through JavaScript calls, and what we'll do is we'll actually go down towards the bottom to see the very last one first, to go and see how we actually set this up. So let me scroll to the point where we actually go and set up all of the elements here. So let's look at what we have in terms of our function that we call, that is the draw scene function. So this is a JavaScript function. It will make a series of WebGL calls to be able to set up the parameters so that we can then render. Okay? So one of the key elements to understand, again, in WebGL is that everything goes through a notion of buffers. So what are buffers? Buffers are set up to efficiently transfer information from the JavaScript context to the hardware context where you expect to be able to go and handle all your data efficiently. And the idea is to minimize the number of transfers between the JavaScript context and the hardware context. You want to keep your data on the hardware as long as possible so that you're not moving content back and forth between main memory and the local memory on your graphics processor. That's key to the performance of what we're doing, and that's key to the architecture in terms of how WebGL is actually implemented. So the first things we'll do here is we set up a viewport where we tell it what the size of the window that we want to look at is. Okay, that's what we're doing on this line. Then we'll clear that graphics context and tell it I want to clear both the color and the depth of it so that I can start a new render. We will then go and use the library that we had defined earlier. You saw that we included a library up on top, which was a helper library to do this, and there is support for perspective matrices through this helper library, which helps me go and build up a perspective matrix directly through this call, so I don't have to worry about doing the math. That's done for me in the library. Then we'll set up our vector transformation matrix to be able to go and move into normalized device coordinates and set that to identity, then move that over through a translation to go and change the origin to where we actually want it to be. And now we'll take that value that we actually have, and we will take that and bind the buffer to it. Again, what this does is this actually sets the values that we've calculated and sends it to the hardware in an efficient manner. Okay? So I'll go through, and we won't go through these as we do them again. Again, we did that once for the triangle. As we get down here, we'll do the same thing for the square, and then we'll go out and do our rendering. So if you look at what the actual call is, it's once we've loaded the actual web page that we're looking at, we'll make a call to this WebGL start function, which will, first of all, find the canvas that we want to draw in. We'll initialize all the graphics library context for that canvas. We'll then go, and I won't go into the details of how this was done. You can look at the code and read Tony's lesson to get more details on this, but basically what we do is we find these shaders. I pointed them out earlier as we were going through the first parts of the code, and we will compile those and send those to the graphics hardware so it's stored locally. Then we'll do the call to the init buffers, which is what we just looked at, to be able to send the geometry over in an efficient manner. Now, this may seem like overkill when you're only doing a triangle and a square, but when you're starting to get very, very high polygon counts or very, very high vertex counts, you find that doing it in this way is an extremely efficient way to actually do it. And then what we'll call is a draw scene method, and that will actually send content over. Okay? So let me go and try to leave this. I have my hardware is not responding right now. There we go. Okay. And as soon as we can leave the screen sharing, we'll go back to the slides. And I see that it's not cooperating, so let me go back and see if I can do this properly here. Try it through another interface. I apologize for this. It's the joys of doing something live. Okay. Eugene, if you can set the slides back to where we were, because I'm getting the spinning pizza pie of death right here on my end.
Let me just push that to audience and see if that works.
Yeah, I'm hoping it will.
Incidentally, to the audience, for those of you who came late, I would recommend that you refresh your screen. That's done either through Control-R in Windows or Command-R on a Mac. This will allow you to have access to the question and answer session, and you are invited at any time to send questions to Alain, which we'll field at the end of the talk.
Right. Okay. So right now we're going through some minor technical difficulties as I've lost control. The screen share is not responding properly. Trying to turn it off as we go, and I'm not getting anything on my screen. Let me go. Oh, okay. I'm getting a message that my Java plugin has crashed. That would explain it. Let me go and refresh on my end, and that should make it work. Okay. There we go. It seems to be back on track. Okay, now I'm not getting a view. Eugene, what are you seeing? Are you seeing slide 11 or 12?
I am at this point seeing slide 12. Perhaps that can be confirmed.
Okay, hold on a second. Yeah, let me go, and I'm just going to go and refresh, and we'll see whether that will get us back on. We're trying to go and do this without a net, and we'll see. Yeah, how interesting. Okay, it's not cooperating. We will try again. Okay, so let me go and see if I can close a couple of my tabs here and hopefully make it. Yeah, it seems happier now. Okay, I'm still not seeing my own slides, so I'm going to try and make this through. And basically what I want to do now is to go on through with WebGL and explain what we're actually seeing. So we've already made the key points in terms of looking at the code, and what we saw was the basic concepts in terms of what we do to accelerate as much as possible to be able to go and not overload the system, because we're not running native code. We are going through an interpreted language, so JavaScript, and we are passing data between this interpreted language and the hardware for the graphics accelerator. And the whole design of WebGL was set up to allow us to do that as efficiently as possible. Okay. Okay, I may have to shut this down and just restart it on my end. Eugene, can you move over to slide 13, please, for me?
Slide, I'm sorry, which slide, Alain?
13.
15.
Yeah, the problem is that, I'm sorry, I think, no, 13, I believe. I mean, I'm having, all I see is the thumbnails. I'm not seeing the full images.
Right now, 15, push to audience, 3.js examples.
No, okay, I'm sorry. It was 13 is the one I wanted. Here we go. No, I'm back. Okay, I think I can do this. Let me get control again, and I have to go and refresh my tab completely there. And that seems to have worked. Okay.
And I don't know if this is part of your voice feed, but your voice is rather clippy.
Oh, okay. I don't know. Well, I'm on my landline, so it shouldn't be, but yep. Okay, I've got everything set up. What we may do is then I'll cut out on some of the scheduled demonstrations. I'll cut them down so we can get back on track with what we're actually doing. So basically, in terms of what we do when we use WebGL, as we pointed out, WebGL is a very, very low-level interface. Think of it as using assembly code rather than using a high-level language. And what we've seen is several efforts to be able to go and layer on top of WebGL itself elements that would build on top of WebGL, so you're still using WebGL, but give you a higher level of primitives to be able to use so that what you can do is not limit yourself to developers who are very familiar with OpenGL ES2, for instance, which is where you would typically look for developers to be able to do web-based applications using WebGL. What we'd like to do is be able to open up the playing field so that more people can adapt to it and start providing 3D content without having to be OpenGL experts. So the efforts there have relied on several approaches. Some of them are declarative, very much like SVG. Others are imperative, so basically JavaScript libraries that are built on top of WebGL to allow users a simpler means of actually accessing all the elements that they would like to. Okay? So I'm going to go and look at two of them for that. So let's go on to the next slide and see. So Three.js is the first one that I would suggest looking at. This one was designed by Ricardo Cabello, and the idea was to go and give users the ability to go and render 3D not only on top of WebGL, but also on top of SVG and various other libraries that you can, so that no matter what, you are able to render, and it will adapt to the capabilities of the browser that you're on. He was solving a problem that people were running into in the early days of WebGL, was that WebGL wasn't widely supported when it was first introduced. So anybody wanting to go and develop for WebGL was up against a major problem that they had to go and resolve, which was how do you go and write your code so that you can adapt to the capabilities of the browser that you happen to be operating under. That's what Three.js was trying to solve. And it's a very, very well-built library. In terms of what it does is it provides you with many helper utilities to allow a web developer, so somebody who's familiar with JavaScript, understands JavaScript backwards and forwards, but may not be an OpenGL expert, provides them with high-level primitives that they can use within their JavaScript environment to be able to quickly and simply create 3D environments. Okay, so that's the goal and what it does. So I put a link to Ilmari Heikkinen's introduction to Three.js, and I would strongly recommend that you go and read through it. It's an extremely well-built introduction, gives you full view as to how you go and use these high-level primitives to efficiently build out 3D scenes and be able to go and have them render on any machine. Okay? So here I've got a series of examples, and I think I'll just leave it to one example so that we don't run into the problem that we had a little bit earlier. I'll go into the lightest weight of all of the elements that we have there, which is the car spin. So why don't I show that to you quickly, and we won't spend much time on that so that we can catch up on what we lost when we had the screen sharing problems. Okay? So let me go over into that tab and share that with you. So you should see it buffering for a few seconds, and then it should start rendering. Okay, so what you should be seeing now is a 3D car in a showroom. And let me show you what this does. So basically what we're doing here is we can actually move around this. This is entirely 3D and available for you to be able to go and show content directly. You've got the ability to interact with this car to be able to show it in different colors. You can change the model of the car. You can go through various elements, various car types, and do that directly interactively. But in the interest of time, I'll cut this one short, and I'll show you another one that I think you will be interested in, which is more of basically a data visualization element. So let me show that to you while we move over. and get that up for you so that we go back into screen sharing mode. And let's see how this looks. So here what we've got is a bar graph in action, which should be coming up shortly. I see that it's buffering the content on output. You should see that quickly, says he, as he tries again. Okay, looks like our screen sharing program may have crashed again. Okay, let me go back to the basic slides, and we will try this back on the slides themselves and see where we can go in here. Okay, let me see if I can push this one to you. There we go. Okay, so now you should see a slide that covers the last API that I wanted to cover, which is X3DOM. So basically this is a proposal from the X3D group, which basically looked at a declarative method. So think again in terms of what SVG does in terms of how you present your content. You extend HTML with 3D primitives that understand scene graphs, cameras, lights, all of the elements that you might want to do with associated helper functions that let you do this. And this basically lets you go and efficiently build out content. And the nice thing about this is that it requires no JavaScript. You can use JavaScript to go and handle your event mechanisms, but it's entirely DOM-based, so it's built on top of the standard document object model, but extends it to understand 3D content. So I'm going to try one simple example with that, and we'll try and keep this easily, which is the Hello World example, because what I really wanted to do with the Hello World example is show you what this type of approach does in terms of the complexity of your code. So let me try and share my screen again with this very simple model, and we'll see how well we can do with that, and hopefully get this up to you in a simple manner. So up into the Hello World example. You should be seeing that come up on your screens very shortly. Okay, so now you should see what looks like a blue square in a white canvas, and the key thing is this is actually 3D, as you can see as I manipulate it. Now the interesting thing is when you look at this, okay, again a very simple model compared to what we've been looking at before, or what you would expect to have in a typical 3D scene. Let's look at what the actual source code looks like. And here what we can do is look at the page source, and so I'm going to go do that again, and you'll see how much simpler this approach is for a scene that is of complexity pretty much equal to what we had in the other one with the triangle and the square. So basically what we do is here in this line we download the CSS descriptions for the context that we want, plus a JavaScript library that will help actually go and interpret all the extensions that we've introduced to do 3D efficiently. What it's doing under the scenes is calling WebGL. But you don't have to worry about it. This is done through the primitives that are done in this part of the code. So let me go and highlight all of this so you can see. That's all it took to go and draw that cube right over there. Basically, I had very, very little things to do. I had to explain what namespace I was operating under. So that's what's happening up here, okay, in terms of where we are with the X3D tag. This sets it up in terms of getting that window that we're actually doing the 3D in. Then inside of that, I have a scene. The scene defines a viewpoint. That's where the camera is. And in that scene, I put a shape. The shape has appearance characteristics, which is where I define a material by defining its diffuse color. And that diffuse color is an aquamarine, which is what we've got with those values that are up there. And that's all I need to do to be able to go and get that shader up there. And then I'm going to go for a primitive geometry and say that the geometry that I'm instancing in that scene is a box. So again, very simple. It's meant to do simple things simply and do it in a way that programmers who are used to manipulating the DOM will feel comfortable with. Okay, so let me go close that one down and suggest that you look at the documentation that I sent over at the x3d.org site so that you can actually follow up if you want more details on that one. And here we're going to keep this one short and sweet to be able to get back to where we were. So let me get that up. So I had a couple of things that I wanted to show, but again, just given how stable the screen sharing is, I think we'll avoid that one now. And we'll just go over to the summary in terms of what we wanted to do so that we can still have some time for question and answers despite the issues that we read. And the key questions you might have is, which of these three should I use, depending on the application that I want to build? And the key thing that comes out of it is if you have programmers who are well-skilled in OpenGL ES2 already, who already understand the concepts and are very familiar with the 3D infrastructure, by all means, use WebGL directly. The key issue that you may run into is that programmers who are unfamiliar with OpenGL ES2 may have a steep learning curve to get up to speed given how much attention to detail you need to provide if you're using raw WebGL. If the programmers that you have on your team or that you intend to hire are programmers who are skilled JavaScript programmers, feel comfortable actually working at that level, I would suggest you look at Three.js. I mean, if they're not skilled graphics developers already, if they're not already game developers, haven't had any experience with OpenGL ES2, they may have difficulties working at that higher level. And the key thing is, since Three.js is already built on top of WebGL, the skills they'll learn with Three.js aren't lost. You can continue to use them for your WebGL development afterwards. For programmers that you may have who feel comfortable in the DOM but don't really feel comfortable in JavaScript, well, you can fall back on X3D. So X3 DOM is the way that I would recommend for those people. So again, the key thing depends on what are the skills of the programmers you have on your team, how much time and effort do you want to invest in terms of making sure that they get up to speed to be efficient on this one, and what are the effects you want to do. If you want to get full access to everything that WebGL does, you need to go the WebGL route. So raw WebGL is the way to go in that case. If, on the contrary, time is of the essence and you don't have the skills on board, look at either X3 DOM or Three.js to see viable alternatives, see what we may do. And that takes us on to the questions. So Eugene, back to you.
Thank you, Alain. There are numerous questions, so I'm going to try to summarize some of them. A fairly large number of questions, and thank you to all the question askers. It's interesting to see the correlations. There's a fairly large set of questions that have to do with importing scene descriptions, geometry, and so on from other formats. Are there a set of utilities that would allow you to do such importing?
Yes, there are. So again, depending on which API level you look at, one of the ones that I found the easiest to use to import legacy data is to go through a Collada transport. So basically take your data, export it to Collada, and then there are Collada readers available for all of the APIs that you can use there. Trying to get a native importer for each one tends to pose a lot of problems. It all depends on the import libraries that you're using. What we found is that the Collada libraries actually are very nice because they not only import the geometry, but they also import the animation. So you can use that. I mean, what I would suggest to anybody looking to import data from somewhere else is first translate it to Collada. That will immensely simplify your life. You'll find that a lot of the problems you would have with proprietary formats actually go away with Collada. Now, then again, you are dependent on what you're using to translate from your native format to Collada. Not all Collada translators are built equally, and you have to take that into account and test to see.
Thank you. Another set of questions has to deal with the comparison of WebGL to a variety of other formats, such as emerging JavaScript 3D work, some new gaming engines such as Fiume and others. Do you have any comments on the comparison of WebGL? I know it's a general question, but the comparison
Sure.
of WebGL to competing.
Yeah, I mean, I would look at these as pretty much religious issues in terms of where you actually look. Basically, what we've got right now is in terms of adoption. So where you can be sure that what you're proposing will actually run on any of the hardware that you're aiming at, so any of the graphics subsystems you're looking at, one of the key issues you're really going to be running into is that the graphics processors that you have, even on your portable devices, are much more efficient than any CPU that you can find to be able to go and do your 3D transforms. They're designed explicitly to do this and do it well. What WebGL is designed to do is to abstract out the interface to that graphics processor so you can be as efficient as possible in terms of getting your data from the JavaScript side. And remember, this is where I was talking about the use of GLSL and the buffer structure. They were designed for efficiency. There are other competing approaches, and they're all worthy. What I'm seeing now is in terms of adoption, WebGL seems to have won this. It's not over yet, but for me, that's where I would bet my money.
Okay, thank you. Another set of questions has to do with performance across the various APIs that are available. Do you have any comments on the relative performance of WebGL versus the competition?
Right. Well, one of the key things in terms of what you're looking at and where the issue tends to come up is it better to make a native application or to deliver your content through a web interface using something, using WebGL or any of the layers on top of it? And the key thing is, one thing you have to understand is as soon as you're doing anything through the web, what you're getting is the generality. Now, again, that's an ideal. It's never fully completed. It's not always 100% exact in terms of all the implementations, but it comes awfully close and close enough that you can actually go and provide your content across multiple platforms with one source. So it's about as close as you can get to write once, run many places as we are today. That does come at a price. JavaScript is an interpreted language. You will not get, no matter how much improvements we've done in JavaScript, it's much faster now than it was in the origins. When we were first starting out, JavaScript was horrendously slow. It's now become much faster, but you're still talking about an order of magnitude difference in terms of natively compiled code and what you would get with JavaScript. You're still paying the price of running an interpreted language compared to running a compiled language with decent optimizers. I mean, compiler technology has evolved immensely. So using that, there's no secret here. You will get better performance and much better performance if you're using directly compiled code. The problem is, to be able to support multiple platforms, you're going to have to compile and optimize for each of those platforms individually. So what you're getting with WebGL is the ability to be able to go and attack multiple platforms at once with a consistent interface and have a reasonable expectation that it will perform properly. And I'm not saying at the level that you would expect from compiled code. We're not there. I mean, there is a measurable difference in performance, but at an acceptable level. So to say, if what I'm aiming to do is to make a first-person shooter, would I choose to do it in WebGL? Probably not. Okay, if what I'm expecting is response times under a 60th of a second and lags in terms of the moment I say I want to do something and the moment it appears on the screen on that same order of magnitude, I wouldn't go for an interpreted language. I would go for compiled code, and I don't know how to make it that efficient without going that way. Now, can I make content that is stunning and impressive through the web interface? Yes, but it's not going to be as fast as compiled code.
Thank you. I think we have time for one final question, and that's several questions have centered around the support for stereoscopic rendering. Does or will WebGL support that?
Oh, good question. I don't know offhand. I believe it does, but I'd have to go and check. I haven't looked into that personally. That hasn't been something that I've been particularly interested in recently, so I can't answer that right now. But I will follow up, look it up, and send that out in the notes that we post online.
Thank you, Alain. Well, there are numerous questions we haven't been able to get to, but it appears that we're running out of time. Apologies for the technical difficulties, but I'm sure you appreciate just the amount of content that Alain was able to present today. I'd like to thank Alain Chesnais again for his very informative presentation and insightful answers to many of the questions. And a special thanks to our audience and their patients for taking the time to attend and participate. This webinar was recorded and will be available online in a few days at learning.acm.org/webinar. You can find announcements on upcoming webinars and other ACM activities at learning.acm.org and acm.org. Also, please fill in the survey by clicking on the URL on your screen, where you can suggest future topics or speakers. This is Eugene Fiume, and I'm saying, hope you can join us next time. Thank you, everyone.